Start that one over. Psi squared is the probability density, which means the probability of finding an electron at a point in space. And so that equals probability divided by unit volume. So the s orbital is spherical. The probability density decreases as the distance from the nucleus increases. Okay, as the thing gets bigger and bigger and bigger, the probability of finding it out there becomes less and less. And when we graph this, the plot looks like a multiple exposure photograph. It's important, though, to understand, even though it kind of looks this way, the electron is not moving around the nucleus like a moth around a flame. It's not just erratically zipping around like Andrew does at home, right? In a sense, the electron's location is spread out over the entire volume of the orbital because it is a wave, okay? And so it's actually spread out all over. So I think there's the graph. So this is a graph of probability density. And this is misleading because it looks like you're most likely to find the electron at the nucleus. And this is graphing the probability density, psi squared, as a function of radius. And it looks like the probability density is the highest right at the nucleus. But is the electron at the nucleus? No, it's not. And so this is misleading. So we get into the radial distribution function. The radial distribution function represents the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. So you can think of this as getting more calculus-like, where they're taking infinitely small slivers of space or of a function or something. You think of an onion and going out successive layers of the onion. This thin layer, what's the probability of the onion, of the electron being found in this piece of onion skin, or the next one, or the next one, or the next one? And this gives us a better picture of where the electron is likely to be found. So the total radial probability at any given distance r from the nucleus is equal to the probability per unit volume, that probability density, times the volume of the shell at that distance r. At the nucleus, r is 0. And so that makes this radial probability very small. As r gets larger, then the radial probability gets larger. And so what we do is we multiply those two functions and we get a better representation. These have opposite trends. The volume of the shell at r gets larger as r increases, and this probability per unit volume gets smaller. R is the further you go from the nucleus. R is getting bigger and bigger. So r is the distance between the electron and the nucleus. When we graph the radial distribution function, we see something like this. It starts at 0 at the nucleus, 0 distance from the nucleus. It goes up very sharply, reaches a maximum, and goes down fairly sharply, and then kind of tapers off. And so this is the region in here where the electron is most likely to be found. This indicates that the most probable distance is 52.9 picometers from the nucleus. And this happens to be the same radius that Bohr predicted based on his model. But there's a very important conceptual difference. In the Bohr model, which is like the solar system, the electron is orbiting around the nucleus. The electron is always at 52.9 picometers from the nucleus. Quantum mechanics says the electron can be found at various radii, but 52.9 picometers is the most probable. That's where it's most likely to be found, but it could be farther or closer. So this is like, let's see. Maybe you think of a dog. So the Bohr model is a dog on a leash. really long leash tied to a tree in the front yard. And that dog is running around at the end of its leash. And it's just at the end of its leash, right? The quantum mechanical model would be more like a dog that is not on a leash, but it is firmly aware of where its home is and where the food is. And so it's most likely within this area where the food and the water are, but it doesn't have to be. Does that help at all? I just made that up right now. Yes?
I'm thinking like if you were to take random pictures of dogs throughout the day, it would be in random spots, like every single picture, right?
Right.
Okay.
So in the quantum mechanical model, the electron is not predictable. But we can say there's a probability that it will be in this area. The most likely distance from the nucleus is 52.9 picometers.
Because of the duality.
Part of it's the duality because if you observe it, then it has to act like a particle, and so it has to be in one place. But it actually is also like a wave, and so when you're not watching it, it's both. It's the wave, and the wave is everywhere. Yeah, it'll make your head hurt. In a good way, I guess. So that's the 1s orbital. The 2s and the 3s orbitals are also spherical. They're just larger in size, but they also have at least one node.
Oh, that was just one orbital?
That was just one orbital. That's the wave function for an s orbital. It has this shape. And so it's almost really like more like a donut or something around, but three-dimensional. So it's like a sphere, but the middle of it, you're not going to find the electron right in the center.
So in each orbital, each orbital has a duality?
Each electron does.
Each electron.
And it can jump from one to another. Yeah. A node, if you take a piece of string and it's fixed at two ends and you wiggle it, so you can get a standing wave. This is the node. This string has three nodes. And these orbitals are wave functions. The larger ones also have nodes. And so the probability of finding the electron at the node is 0. That's where the wave function goes through 0. And then it goes down, and it goes up, and it goes down. It looks like, no, there wasn't something missing there. Okay. So if we look at the 2s orbital, we see that there is, this is the probability density, which we said wasn't really a good picture of how the electron was distributed because it goes to infinity basically at the nucleus, and that's not right. This is the radial distribution function, or the radial probability. And so we see this little bump here, and then there's a place where it goes to 0, that's the node, and then it goes back up again. So if we look at the outside of a 2s orbital, it looks pretty much the same as the 1s, just bigger. It's a sphere. But if you cut it open, you see that there's this part here in the middle where the electron is not found. It might be right here close to the nucleus, but it's mostly going to be out here, but it's not going to be in here. And the 3s orbital has two nodes. So each principal energy level has one s orbital. It's the lowest energy orbital in a given principal energy state. It's going to be spherical, and the number of nodes is going to be equal to n minus 1. So the 1s orbital, where n equals 1, has 0 nodes. And the 2s has 1 node, and the 3s has 2 nodes, etc. The p orbitals are a little more complicated. Isn't that great? Each of those energy states above n equals 1 has 3 p orbitals, m sub l being minus 1, 0, or plus 1. So we get 3 orbitals that point along different directions on a three-dimensional axis. We get x, y, and z. And these are two-lobed, and there's going to have one node at the nucleus, so a total of n nodes, because there's 3 orbitals, they each have one node, so we have 3 nodes. And this is what the p orbitals look like. So this is more of a, multiple exposure photography kind of deal, where for the px orbital, it's lined up along the x-axis, and there's going to be a region of probability on one side and on the other side, but it's not going to be found at the nucleus. And if we look at it as more of a solid structure, it would look like this. It resembles 2 balloons, right? And this is the radial distribution function. We see that it goes up and comes back down. And so here it's starting at 0 and going up and coming back down. And that's where you get the shape. So we've got one along the x-axis, there's my arrow, one along the y-axis and one along the z-axis. The d orbitals are found in principal energy level 2 and above, and there's 5 of those guys, and we've looked at those quantum numbers, m sub l, the angular momentum, there's 5 of them. Each of these represents a different orbital. And so we've got dxy in the xy plane, dxz in the xz plane, dyz in the yz plane, and dx squared y squared. I don't even want to go there. And then the 5th one is along the x-axis. So 4 of them have 4 lobes, and the other one is called a 2-lobed toroid. These have planar nodes. In higher principal energy levels, then they add spherical nodes as well. Yay! We didn't even want you to tell us that. This is what they look like. So they resemble a little bit the p orbitals, because they've got this kind of balloon shape. But instead of just 2 lobes, there's 4. For this one, this one, this one, and that one. And so this guy is in the YZ plane. He's vertical. This one's horizontal. This one is going back and forth. And then this one's horizontal, but tipped from this one. So they don't overlap with each other. And this is the really weird one.
Do we have to know specifics for the test?
No. I want you to recognize the shapes of d orbitals. Like if I showed you one of these things with 4 lobes or this guy, I'd like you to know that that is a d orbital, but I would never make you draw them on an exam. Okay? Yeah, that would be mean. And I am many things, but I am not mean. F orbitals, things just get bigger and complicated, more complicated. So now we've got 7 of them. And these are 8-lobed. Isn't it interesting how these patterns? The s orbital is just this one thing, and then we've got 2 lobes and 4 lobes, and now we've got 8 lobes. Every atom has these orbitals. Every atom has these. And these have planar nodes, and again, some spherical nodes at higher levels. And this is what the f orbitals look like. Right? Yeah, so these guys are weird because they've got this big node, planar node in the middle. Yeah. And this guy's going the other way. Yeah. Looks like very weird balloon art. These orbitals are derived from mathematical wave functions. And wave functions can be positive or they can be negative. And they can also have nodes where the wave function is 0. And so we call the sign of the wave function its phase. So just like when we talked about waves on water or waves of light being in phase or out of phase, the waves of electrons can be in or out of phase. When the orbitals overlap, they can be in phase, meaning they have the same sign, or out of phase is opposite in sign. And this is going to be really important in a later chapter when we talk about bonding, about these waves being in phase or out of phase, constructive interference or destructive interference. So an s orbital doesn't have a node, the one s orbital, and so it's just either plus or it's minus. The p orbital has one node, and so one side of this will be plus and one side will be minus. But you could also have the 2p orbital with the opposite phase. Right? The opposite phase would be like this. And the opposite phase for this one would be like that. So if you had two 1s orbitals that overlapped and were out of phase, they would essentially cancel each other out. Well, the phase is like the phase of a wave. It's, where is it big and where is it small? If they're big in the same place and you get them together, they grow. Becomes more probable that things will be there. And if they're out of phase, then they shrink down to nothing. So after looking at all those funky shapes, why are atoms spherical? Well, we depict them as spherical because if we take all those orbitals and superimpose them, they basically make a spherical shape. So in here, they've taken all those different orbitals and superimposed them. And so the overall shape of the atom is spherical, even though it's made up of all these funky balloon shapes.